We continue with the Euclidean distance for the quadrature amplitude modulated signal, and we said that our signal, as if I write it here, our signal can be expressed as a combination, of the scaled version of phi 1 as a summation of the scaled version of phi 1 and phi 2, right? And this scaling, this scaled version or this scaling, for Sm we can say that, okay, suppose this is Sm1 of t and this scaling is Sm2 of t. So our Sm in the vector form is Sm1 and Sm2. Now, we already discussed the Euclidean distance and expressed it. We derive an expression for it. We can have a special case. Let's discuss a special case. A special case for the Euclidean distance, and in this special case we assume that these phi 1 and phi 2, which are actually the orthonormal basis function or the cosine carriers, the cos 2 pi f ct and the sine 2 pi f ct, they are scaled by Sm1 and Sm2. And suppose this Sm1 and Sm2, this Sm1 and Sm2 takes the discrete values which are given by 2m minus 1 minus m. Suppose it takes these discrete values where our m is 1 up to capital M. Suppose it takes these discrete values, right? 1 up to capital M. So if it is now if you recall your pulse amplitude modulated signal, we had taken these amplitude levels. So if now we are taking these amplitudes level for Sm1 and Sm2. So if in this special case, if we said that these amplitude values are used, so for if you are using M1, you can see M1, this value is 2 minus 1, which is 1 minus m, right? This value is 1 minus m. Similarly, another value for M2, it would be 3. For 2, it would be 3 minus m, and so on, when it is capital M, the value would be 2m, 2 times capital M minus 1 minus m, so it would be m minus 1. So these are the possible values, and we assume that it takes these values as in the case of pulse amplitude modulated signal. So in that special case, if these are the amplitude values, which turns out, these values actually turns out to be, if you go back to your amplitude modulation, it turns out to be these values, right? It turns out to be these specific values, where we have the last values. If you see, these are the specific values for this one. So these are plus minus 1, plus minus 3, plus minus 5, and so on. The last value is the plus minus m minus 1, right? So you can say minus 1 plus minus m minus 1. So if you have m4, it will be plus minus 1 plus minus 3 only. So you have 4, similarly, and so on. If it takes these values, these specific values, so the two Sm1 and Sm2 takes these specific values, right? If SM1 and SM2 takes these specific values, then we can say that the Euclidean, we can find the Euclidean distance, and we would see that the Euclidean distance would be 2 times Eg. This is the expression which we found for our pulse amplitude modulated signal, this Euclidean distance. And you can verify it. Just try a little bit with this constellation. Let's try this one. Suppose you have just 4 amplitude. I'm just restricting myself to 4 amplitudes level here and 4 amplitudes level here, right? For phi 1 and phi 2, just 4. So this will be plus 1 plus 3. This will be minus 1 minus 3. This will be 1 3. This will be minus 1 minus 3, right? So if you see the signal points, your signal points would be this one, this one, this one, this one. Similarly, you have this point here, this point here, a point here, a point here. These are your signal points. 1 point here, 1 point here. So we have 16 signal points with these amplitude levels, right? Now each carrier which is phi 1 and phi 2, if you observe each carrier, and these points are now in Euclidean space. So if you find the distance, if you find the Euclidean distance here, we can say that if it takes these values plus minus 1 plus minus 3 and so on, if these are the values taken, discrete values taken by the signal amplitude on both the orthogonal carriers, the Euclidean distance, the minimum Euclidean distance, you can always find the distance between 2 points by using that expression, right? But the minimum Euclidean distance, which we say d min would be equal to 2 times Eg under the root 2 times Eg, right? This is the minimum Euclidean distance which you can verify. You can always verify this minimum Euclidean distance, right? I hope everyone can do it using your previous knowledge of the pulse amplitude modulated signal. For some specific case, if you are interested, just try this one. 1, 1 and 1, 3. Just take these 2 points and try to find out the Euclidean distance using the above expression. The Euclidean distance between m and 2 points, right? So what is the Euclidean distance? Eg over 2. You have am. Let me specifically mention this point minus this point square. So 1 minus 1 square plus this point minus this point square, 1 minus 3 square. So if you square it and you try to solve this one, what do you get? Eg over 2. This is 0. I have used this expression just as I derived it in the previous video. This is here it is 4, right? 2 square. So you are left with the Euclidean distance. dmn, which is under the root 2 times Eg. This is just a simplified expression. We use this one, and this is the same as the expression which we derived in our previous video, that we can DMN. This is actually now minimum Euclidean distance because we are taking the adjacent signal points. You can always take other points, and those that distance will be greater than this value, right? This is the minimum Euclidean distance. We just use to find out the Euclidean distance between 2 points SM and SN. We can use the expression which we derive, AMI minus ANI square plus AMQ minus ANQ square. So this we use this expression, right? We used this expression. So this is the same as this one. And we came to know that if we take the adjacent points to closer, the points which are closest to one another, the points which are closest to one another, we get this Euclidean distance. We get this Euclidean distance, which is given in this expression. That for the closest points, this is the expression for Euclidean distance. Other would have greater distance, right? So this is how we can have this for the special case. For the special case, when it takes the amplitude plus minus 1 plus minus 2, our minimum Euclidean distance would be 2 EG, 2 times EG for the QM symbol. This is the for the QM symbol. So minimum Euclidean distance in the constellation will be between the signal points would be under root 2 times EG. There is another special case as well, which is related to the rectangular constellation. So another special case is related to the rectangular constellation. Rectangular constellation of QM. Rectangular constellation of QM. And if you observe the rectangular constellation of QAM, it looks like this. The rectangular constellation actually look like this. If you see your rectangular constellation, your signal points are on rectangle. For example, you have an inner rectangle, here, and then you can have you can have an another rectangle here. I can draw it another rectangle here, and so on. So your signal points are usually on these rectangle. So these may be 4 signal points, right? So and for M4 you can use this. This is the signal points for M4. So we have M equal to 4, just in a rectangle. Similarly, if you have an outer rectangle, you can use more signal points, and those can be those signal points can be here. You can have a point here, and 1 point here. It's on these rectangles. You can see here another point here, another point, another point, another point here, and here. Now if you observe here, for M16 we have 4 points in the first quadrant. Similarly, 4 points in the second quadrant, 4 points in the third quadrant, and here these are placed so that you have 4 points on the outer quadrant. You have these 4. They are placed in such a way that they maintain the minimum Euclidean distance of the adjacent symbols, right? So the minimum Euclidean distance of the adjacent symbols should be maintained in this rectangular QM. Now, if you have this type of you can draw other rectangles as well, and you can see the higher values of m. Now in this special case which we are discussing, in this special case, if the if capital M takes value which is 2 raised to the power 2 times k, right? If it takes these values, where, and what is k? K is just integer 1, 2, 3, right? So what would be the possible values of m? Possible values of m would be 4, 16, 4, 16, 64, 256, right? So these are perfect squares. If you see 4, you can take the square root 2, 16, take the square root 4, 64, you can take the square root of 64, which is 8. So these are perfect squares, right? Now these are the possible values of m. When you have when these values of m are when m takes these values, when your m takes these values 2 raised power 2 times k, the signal and the amplitudes of the signal, and the amplitude of the signal takes these values plus minus 3 up to plus minus, because you have it on both sides, plus minus square root m minus 1, square root m minus 1. So both sides, these are the amplitude values. You can just verify it, take any value of m, for example this one or this one, and you can just find out the amplitude values which are given in this by these specific values. So this is the special case when m takes these values and the amplitudes are given by plus minus 1, plus minus 3. Usually in simulation we use these particular values. Then the average energy, if you observe the expression for the average energy, but we derived the expression for our average energy. We said that our expression of the average energy is the square Sm square, and that is Eg over 2 AMI I square plus AMQ square. We derived this expression previously for the energy of the signal. So if you observe the energy of this signal, the average energy in this case, it turns out to be the average energy, because when we try to find out the average energy, what we actually do, we sum all the points, the energies of all the points, because in this signal constellation all the points do not have same energy. Different rectangles, the points have different energies, right? So to find out the average energy, what was our procedure? We try to find out the we sum the energies of all the signals for all m, right? We sum the energies of all the signals and we divide it by the total number of the all the symbols, and we divide total number of the symbols, which is m. We have m number of symbols. So this is how we derive the expression for the average symbol energy. So if you do it for this one, you can rewrite this expression for the average symbol energy for in this special case for this particular case as 1 over m divided by total number, and the summation for all m, right? But here we have two variables, m and n, so actually we have two summations also. Eg over 2 is still there, it's a kind of constant, and we have a summation for all values of m, because we have this part, and we have another summation which is this is n for all values of n, right? We have another summation which is for all values of and instead of, now I can drop this I and Q, just M and N are enough to for differentiation. So AM square plus AN square, right? We can just write our expression in this form. We can write our expression in this form, which gives us the uh, expression for the average symbol energy. Now all values of M, if you observe, the all values of M and N, they actually varies from 1 up to square root of M. Similarly, it is 1 up to square root of M. So all the values are just on any axis. If you observe for this special case, these are square root of M. Square root of M, all the values. So in the rectangular QM, for example, in the rectangular QM, just go back to your rectangular QM. For example, Q16, just observe M equal to 16. So if you observe M equal to 16, here this is M equal to 16. So if you observe M equal to 16, square root of M is 4, and you can see that this any axis has only 4 different amplitudes, which I'll mention here. You see, one amplitude is here, this one, another amplitude, another amplitude, another amplitude. It's not perfectly drawn, but you can see it. We have just square root of 4 values. You have just square root of M values. M is 16. We have 4 amplitude values here. This one, this one, this one, this one on x-axis. Similarly, or you say that your cosine carrier can take plus minus 1, plus minus 3 values only. Similarly, you have 4 amplitude values, which is under root M. You have under root M amplitude values on the y-axis, these 4 only. So plus minus 1, plus minus 3, right? So these are the particular values which are square root of M. So we can write our expression. Just in this form. Now I hope this would be clear. I hope that this expression would be clear now. This double summation would be clear. We have just for all M and for all N, we can write our expression in this form. And if you try to solve it, you end up with a simplified expression. I'll just write the final expression, which is M minus 1 over 3 times Eg. This is the average symbol energy of the square QM constellation. So if you have a square QM constellation, this is the average symbol. This is the average symbol energy of square QM for this special case when your M takes 2 raised to the power 2k values, and the values are plus minus 1, plus minus 3, and so on. So this gives you the expression. This is the expression for your average energy. Now when we have the expression for average energy, we are always interested. If you have the expression for the average energy, which we said that this is M minus 1 over 3 Eg. This is the expression for our average energy. We are always interested in finding out the energy of the average bit energy, which we represent by EB. So the average bit, whatever the number of bits it carries, right? So we have to divide our average energy by the total number of bits it carries, which is log m to the base 2. And this would your expression comes out to be 3 log m to the base 2 times Eg, right? So this is your expression for the average bit energy. And if you want to find out the minimum Euclidean distance, the minimum Euclidean distance, uh, the minimum Euclidean distance, the minimum Euclidean distance, which we say it is 2 square under root 2 Eg, just as we derived in our expression. So we can have the expression for minimum Euclidean distance, and that would be in terms of EV, right? We solve this EG, we solve this EG equation, this one, in terms of we want to write it in terms of EV. So it would be 2 times EG, and EG is actually 3 log m to the base 2 over m minus 1 times EB, right? So this is your expression for the minimum Euclidean distance in terms of average bit energy. So we we end up over here. You have the expression for the average bit energy, and if we want to see our QM modulator, actually it's very simple. You just need the sequence. You just need a mapper. Actually, you just need a mapper which maps your all m. For all m symbols, you just need a mapper that would choose the values am, right? That would choose the values am, the amplitude values, which has actually 2 parts, ami and am. It has another another part, amq. Now this ami is multiplied with the basis function, which is phi1 of t, and the amq, if you observe amq, it is multiplied with another basis function, which is phi2 of t. And if you add these two, just an adder, if you add these two, you get a Sm of t, which is your QM modulated signal. So your modulator block diagram is very simple. You just need a mapper, which you should have bits, right? You are always having bits, and just group these bits for M16. Suppose we are having M16, so we will group it in 4 bits group. So this mapper has to based on these first 4 bits, it will choose the am, each symbol, SM or AM, you can say, and then each symbol has 2 coordinates, right? AMI and AMQ. So those 2 coordinates are multiplied with phi1 and phi2, which are the sinusoids, and the addition gives you the QM. This is the QM, simplified QM modulator. So just go through the text and try to do it try to solve these equations by yourself. Write it yourself on a paper, and hopefully we will see the simulation later on, that how to simulate this QM modulator. You'll see the octave code for the QM modulator in the most probably in the next lecture or next video. Just try to cover it up, do all these analysis, and I would require you people to prove each and every equation.